So our next session is going to be static analysis and program safety with Sunny. Can we get Sunny up? Hey, how you doing?
Hey Sai, I'm doing great. How are you?
Yeah, good. Looking forward to the session. I think static analysis in editor has been a big thing for me in terms of just having something there running, telling me what I'm doing wrong while I'm coding. So interesting to see what else is new. So I'll hand it over to you.
All right, yeah, it's great to have some your friend telling you all the bugs even before you have committed your code. So I think static analysis is a great way to find bugs early. All right. Um, Hello, everybody. My name is Sunny Chatterjee. I am an engineering manager in the Visual C++ team at Microsoft, where I'm lucky enough to lead the static analysis team. And today I'm going to talk about everything that I learned working on static analysis and C++ program safety over the last several years. I'll share a lot of learnings with you. So let me get started by going into why C++ code safety matters. I'm going to start by quoting Bjorn on this. Last year in CPPCon, Bjorn did a talk on type and resource safety in C++, and he had a paper as well on it, where he mentions that complete type and resource safety have been an ideal aim of C++ from very early on. So at Microsoft, we believe that great customer experiences, they start with quality. You can have you can write a feature that is, you can write ship a software that is loaded with features, but if the piece of software crashes or hangs, if it has poor performance, or if it has security vulnerabilities, it's unlikely that people are going to love that product. And it turns out that you need more than the language and the compiler to be able to write great software. You need some judicious programming rules that you get from the C++ core guidelines. For those of you that haven't checked this out, it's available in the ISO CPP GitHub repo. You need a guideline support library to enforce some of the guidelines through type extensions. Microsoft maintains its own guideline support library in GitHub. It's an open source project where we welcome contributions from the community. You need static analysis tools to enforce the guidelines and find defects early, even before you have committed your code. And you also need good dynamic analysis tools. For those of you that haven't checked out, do check out MSVC's address sanitizer. And you need runtime checks to be in place in case you have introduced some security vulnerabilities in shipping software. You do want to cater to them at runtime. So for today's talk, I'm going to focus on the first three topics, which is core guidelines, guideline support library, and static analysis, and how we have been using these to make C++ safe. So before I head into the specifics, I want to talk about what is static analysis. So let me start by sharing this article from The Economist that came out almost a decade back. It's called Building a Better Bug Trap. Essentially, it talks about a bug which costs $1 to fix on the programmer's desktop would cost several hundred once that bug is incorporated into a program. And it will cost many thousands of dollars more once the bug has been shipped with your software and that software has been deployed in the field. This is where I think static analysis becomes extremely important because it finds bugs in programs at compile time. What it means is that you will find these issues even as you're typing your code, or you're building, or you've say spun off a PR code review, and you will find these bugs at your fingertips. It applies some clever techniques to look for specific bug patterns in your code. And it's a complementary technique to traditional testing and runtime checks. It's not a substitute for them. Saves a bunch of dollars for the company, which large corporations love. So let me give you an insight into how we have integrated safety checks in the shift left experience for developers. I I'll first start with our native Visual Studio experience. So this is a snapshot of Visual Studio. So every line of code that I shared today has been picked up from some production software that we have looked at. So in this particular example, you will find that Visual Studio has pointed out some green squiggles in the code. Specifically, I would say that one of the objectives for us was to make sure defects show up in almost real time as green squiggles as you're typing or saving your work. And defects should be easily understandable. And there are a few highlights down below. Let me double click on that. We have this feature called key events that shows up in the error list. It basically gives you the thinking behind the analyzer, why the analyzer believes there is a bug here. So for this particular example, the analyzer is complaining that p context can be null. And it gives you the reasoning why it believes so. So if you follow the reasoning, like line 70, it's initialized to null. On line 18, the branch is actually entered. The not p connection is assumed to be true. So p context is never initialized to anything other than non-null. And then on line 26, you are dereferencing that, which results in a null pointer dereference. My second slide would give you an insight into how we have integrated these same checks on GitHub. So if you are working on GitHub, we have a GitHub security action where you can go to your C++ repo. And if you are working a CMake-based project, you can go to the security tab and go to the code scanning alerts. And you can set up code scanning for your repo. When you select code scanning, there are a bunch of code analysis actions or code safety actions that you will find. There's one from my team called the Microsoft C++ code analysis action. And you can click on that, set up this workflow, and it's configured for your repo. Here is an example of the same code. When I ported that over to GitHub, you now see that that warning in the GitHub visualizer. And there are a couple of interesting things happening here. You find this warning embedded in the same way like a regular user comment in GitHub, if you're familiar with that. It shows you a dismiss box here where you can dismiss this warning and mark it as a won't fix, or you can fix this warning and resolve it. There is another interesting box here called show paths. And if you click on the show paths, it basically gives you the same reasoning that you just saw in Visual Studio in the GitHub. It brings up a separate window where you can follow the reasoning of the analyzer step by step, why it believes there is a bug in the code. So we believe that this kind of experience is an ideal way to shift left, because you now have an action for the whole C++ community that's publicly available. You can go read about this action in our team blog, where we blogged about it around last CPBCon. If you want to learn more about code scanning in GitHub, you can go. You can maybe take a snapshot of this slide. I have given some links here. You can view results in the GitHub visualizer. You can easily integrate your own analysis tools, because it's all driven off a standard static analysis log format called Sarif 2.1. It's a standard format based on JSON. And as long as your analysis tool produces that format, it's super easy to integrate into the code scanning alert in GitHub. So if you are a maintainer of an OSS project, give this a try. It's free for all public repositories. And as you saw, it automates running static analysis in the PR workflow and surfaces all the results to the engineers before their code is merged. If you are working on a private repository, you can read more about the offering from GitHub Advanced Security page. And most recently, we have also integrated static analysis in the Compiler Explorer. You can now select the latest MSVC tools drop and select static analysis from the tools menu. And we have seen that Compiler Explorer is a great way with which we interact with developers. Like, it's great for getting repros back with a small tiny URL. It's also a great way where developers can try out our latest offerings, the latest checks that we blog about. So I'm excited about the fact that people can now quickly try out these checks in Compiler Explorer. before deploying that in production environments. So you can find that the same warning on that code now shows up inside of the compiler explorer. So next, I'm going to switch my focus into the learnings and evolution of running static analysis. So a lot of what I share today will be real world code in production software. And I want to keep the authors of these code anonymous. So for today, for the rest of the talk, Peppa is going to be my author. So there is a cute little picture of Peppa Pig on the right-hand corner of my slides. And let me just start with the very first days of running static analysis at Microsoft. So we started with Lint-style checks. What Lint-style checks are, they are basically checks that find defects quickly. These defects are pretty cheap to locate and fix. And these are built on syntax trees or simple, slow analysis. And there have been many successful lint checks that are available in the market today. So we have a bunch of happy customers using this Lint-style checks. So let me give you examples of what these Lint-style checks look like. So here is an example where, again, it's like a piece of code from production software where you have a function foo and something funky is going on in this function where x is a union. I've just defined x as union containing two pointers, one to a void star and one to a y star, where y is a different structure. I don't have y defined here. But there is something going on in this line that I have highlighted in red in this function. Let's check out what's happening here. Let's start from the beginning. So on the very first line highlighted in blue, we allocate a new union object x, assign it to this px. We assume that condition to be true. So we are reading in a string from an external stream, and we are assigning that string to the PV field of the union, which is a void star. And way below in the code, we forget that the valid field of the union is PV, but we forget that, and we end up referencing the field PY of the union. And that ends up calling a function f, which is essentially fed by this string. So an attacker can easily control the function that you're calling in this particular case. And that's a pretty nasty vulnerability. So it turns out that you can write a very simple Lint-style check to identify patterns like this in your code. So you can inspect the syntax tree and say that, hey, whenever I see a union that uses multiple type pointers, it can cause this kind of type confusion attack. So I'm going to forbid that in my source code. So here you can see there is a warning that says, don't use a union with multiple type pointers, use a variant instead. And that is, in fact, also a specified rule in the C++ core guidelines. Under the type safety profile, there is a type.7 rule that exactly asks you to do that. Now, it's a simple Lint-style check that came to the rescue, and Peppa is pretty happy about that. She can prevent new code from having the same kind of errors in her code base now. So what you just saw in the previous example is a type confusion attack where unions with multiple pointer value are vulnerable, especially when one of those depend on external conditions. You can easily lose control, and it's remarkably common in production software. Mitigation is also pretty simple. You basically ask programmers to use a stood variant instead of these naked unions. And by writing a Lint-style check and enabling that check in your inner loop, you prevent new code from having the same defect again once you've fixed it. And it's also supported by the C++ core guidelines. Let's look at a next example of another Lint-style check. Here, getIndex is a function which takes a pointer to an integer and called buff and an integer buff size. And our interesting function is fetchElement, which also takes pointer to an integer buff and an int buff size. And we call the getIndex function and return the buff index. So essentially, it's basically reading into a buffer. So let's see what happens when we run static analysis on this code. We get a warning saying that symbol buff is never tested for nullness, and it can be marked as not null. The reason static analysis gives you that warning is because it figures that for buff index to be a valid access, which is a dereference into a buff at an index offset, it should be non-null. However, it cannot prove that buff is not null. Its nullness is unknown at the point of dereference. So it tries to enforce that star buff the index to be valid operation, buff must be not null. And it's asking the programmer to specify that in the function. So it's an easy bug, but often difficult to track down later. But you can see here that it's easy to determine these bugs with simple flow-sensitive analysis. So what Pepa does here is she goes and adds a null check. She checks the buffer to be non-null, and then she does the access into the buffer. And that way she has been able to safeguard against the null dereference issue here. Again, this proves that Lint-style checks are easy to locate and cheap to fix. So let's look at the next challenge. How can we scale these Lint-style checks? That's been our challenge. So there are the Lint-style checks are great in finding simple to detect errors in your code by looking at the syntax trees, doing simple control flows. But we need to do more. We need to analyze across the function boundaries because we want to get a full overview of the program to be able to find deeper bugs, deeper semantic issues in the code. So there are two ways to do that. One is the interprocedural analysis, where we often call it as a whole program analysis, where we start with some leaf level functions, we try to build the function properties, and we propagate that across the call chain. Because we are doing a lot of work here, this kind of analysis is slow, and for a large production code base can often take days for the simulation to run. So this kind of analysis is ideally suited for the outer loop. Like once code has been merged, you can run this kind of analysis in the outer loop and file bugs that developers can go back and fix later. Again, it's great for specific problem domains. Like we have very successfully run a global analysis tool at Microsoft called Prefix, which was great in finding use after free class of errors. There's the other approach to doing whole program analysis, which is called intra-procedural or local analysis, where we try to analyze across the function boundaries, and we look at each function in isolation. The challenge for us is we can't see across function boundaries, but we try to infer the semantics of the calls by looking at several different properties. Like we can look at the types of the parameters, we can look at the types of the function return type, we can look at type extensions. So for those of you that are familiar with Microsoft's implementation of the guideline support library, we have a bunch of type extensions there called the GSL span, or we have a GSL not null. So we can use these type extensions. We look at modifiers. So if you have a const modifier, for example, to a pointer parameter, the tools can assume that chances are that pointer is not going to modify the data because it's marked as const. We can use heuristics. If we have nothing but a raw pointer to a pointer parameter, the tools can assume that maybe it's reasonable for us to treat that pointer as it's maybe readable from and writable to, because there is no modifier on that. We can assume that to be an in-out in its semantics. And we also put in a bunch of source annotations. At Microsoft, we have been using Microsoft SAL for a number of years, where we can describe properties of the function contract in a formal way. And these source annotations have been great in bridging the gap between local and global analysis. So we can convey the behavior of the function call to the caller by using these annotations. This kind of analysis is pretty fast. Like you can get results order of milliseconds or seconds. So it's ideally suited for being a loop. So you can run it during your development, you can run it during the PR. Essentially, you can find bugs using this kind of analysis before your code gets merged. And it can find issues across a wide range of problem domain. So our focus for today will be on the intra-procedural or local analysis, where we analyze each function in isolation. So let's look at the same previous example that I showed you for the Lint-style checks. The same example, and you saw that Pepa, our programmer for today, she added the null pointer check on the buffer, and she ran the static analysis tool one more time. And she found the different warning this time around. This time, the analyzer issues a warning that says buffer is there is a possibly incorrect single element annotation on the buffer. So buffer is assumed to be of 1 byte in length. And so there is a potential overflow when you're using the expression buff index. Now, This is confusing because paper does not know why the analyzer believes that buff is of size 1 element, because there is nothing here that says that. And so what paper does is she goes and does a search for all the colors of the fetch element, and she realizes that buff is not of size 1 element, but all the colors make sure that buff is at least as large as buff size before they call fetch element. So the buffer size here is not 1 element, but of buff size element. For anybody looking at this function in isolation, it's very difficult to figure out how that pointer to an integer parameter and that integer buff size, they are related just by looking at this function. So once Peba convinced herself that yes, this buffer is of in fact buff size and not 1 element, she had the next challenge, which is how do I express that? How do I express that in C++? Because C++ does not really allow you to express buffer sizes. So the challenge for Pepa now is how to express buffer sizes in C++. So she magically chances upon this header in the Windows SDK called sal.h and figures out these cute little annotations. One of those annotations is called inReads, and it is exactly what she was looking for. Here, inReads buff size essentially tells the analyzer, hey, buff is of in fact buff size and not 1 element wrong. So Pepa uses these annotations in her code and reruns analysis, and then she stumbles upon something else. She gets a new warning from the analyzer that tells her, hey, there is a potential read overflow happening here using the expression buff index. And the analyzer tells that the buffer is actually unbounded by the buffer size. In fact, in particular, the result from the get index function call is not constrained by the buff size. This is in fact an actual potential buffer overflow that's been found, because as you can tell, get index can return any size t. It may not be bounded by the buff size. So if you just use that blindly without checking that the index is bound by buff size, you will end up accessing the buffer out of bounds. So using this sal, we were able to find this real buffer overrun in the program. So Pepa is somewhat happy that she's found a real bug before it escaped to the hands of the customers, but now she's debating whether she has to learn a new annotation language and these cute little esoteric notations. And so the challenge for us is, before we solve the next challenge, I just want to touch upon this, like advantages and disadvantages of this annotation-based approach. So annotation-based approach is great for formalizing your code documentation, improves static analysis, gives static analysis tools a chance to read these in a formal way, improves the API design, because you want to be able to express the contracts of your API so that the callers can use these APIs in the right way. So you can think of annotations improving the design of the APIs. And it provides a lasting and incremental return on investment. As you add more annotations to the more vulnerable parts, buggy parts of your code base, you get benefits out of that right out of the bat. That said, there are several disadvantages to using annotations. They are non-portable. If you're working across different tool chains and sharing code, you can't port these annotations easily. They're viral in nature. They would quickly explode in the source code as you propagate them across the caller-callee chains. And they're not the ultimate source of truth, because if your code evolves and if your annotation has not been updated, then the annotations can quickly go stale. And it's only as good as the tools. If the tools are not able to make sense out of the annotations and take advantage of them, then there is no point in spending efforts annotating your code. So the challenge here for us was, can we do better than sal annotations? And the next slide gives you an answer to that. We worked on this type called GSL span type, which is available as a type extension in the Microsoft GSL library in GitHub. In C++20, we also have this in the most C++ standard form called the stud span. And what GSL span encapsulates is a pointer parameter and its extent in a single encapsulation. And it does not have its own memory allocated. It's just a view over a contiguously allocated memory. So anytime you're passing a contiguously allocated memory, if you use this GSL span type, what it does is it automatically provides that beginning pointer and size information to the tools to figure out buffer overruns at compile time. Not just that, it also gives a chance to the runtime checks to also verify that the buffer that you are accessing is within the bounds of that span, because as you pass the span, the extent of that buffer is always known to the compiler toolchain. So by using this span type, Paper has now finally able to use a type that is range checked at runtime. So even before that if guard that you see here with my blue arrow, this code is safe. Without the if guard, we would want statically saying that index is not bound by the indexes will not be bound within the sizes of the buffer. But even if you forget to add that if guard, your code is safe at runtime because you now have a way where the runtime can check that if the access is within the size of the span, and if not, it can terminate your program. So type and type extensions are really great because first, they are portable. They can work across different tool chains. They are checked by the compiler. And suddenly, runtime checks become possible. So even if you've managed to ship software with some security bugs out there in the field, you will find that your runtime checks can add a layer of safety. So Pippa is happy because she's now seen these modern C++ types and discovered that these types and type extensions are a great way to write safe and reliable C++. With that, that brings me to the end of my learnings by working on static analysis over the years here at Microsoft. And with that, I'll leave you with a number of ways you can join the fun. As you've seen, code analysis finds bugs. It's free, and so you should use it. If you've not seen these tools integrated into your developer environment, and if you happen to have an engineering systems team, talk to them. Make sure that code analysis tools are part of your shift left experience, where you type, build, and create PRs. Why should you use it? If you're not convinced already, I can share some anecdotal experience that I did in the past few slides. Been in use at Microsoft for nearly 2 decades. They've validated millions of lines of code in production software. Static analysis technology has evolved over 10 years of it has over 10 years of research into it. It's available in all editions of Visual Studio. It's available in GitHub Actions, Compiler Explorer. Internally at Microsoft, we have a few tools called OACR and Guardian. So all of them have static analysis integrated into them. And it's also a US executive order regulatory requirement here at Microsoft. So in March, we did a big security push by fixing static analysis bugs. We actually fixed about 1,000+ bugs in Visual Studio Codebase in March. So what's next for the team? We want to invest into more and more safety checks. It's, our mission is to make sure that C++ is a safe language to use, and we have been making efforts to putting out checks there that will find some of these bugs in real time as you type your code. So we'll revise the buffer overrun checks because the current implementation is somewhat noisy. There is null pointer dereference that we are improving. We have been working with the security team at Microsoft to detect arithmetic overflow in allocators. And that check has been very successful internally. So at some point, we'll actually put that out in the open. We have been writing checks for determining memory leaks, pointer safety, stood optional exploits. Our lifetime checks are experimental. We do want to move that out of experimental into production ready state. Also do check out our Microsoft GSL repo, where we work on these type extensions and interact with the community. We made a release at the beginning of the year. So we have a blog about GSL 4.0. We want to support new language features. We want to make sure that as new language features gets invented, like coroutines, for example, you have new ways of introducing bugs. Like with coroutines, you can run into lifetime issues. And we added a bunch of static analysis warnings that will detect these lifetime issues when you're using coroutines. With modules, we want to make sure that the static analysis artifacts are exported and imported across the module boundaries. We also want to create static analysis tooling around modules. And there will be upcoming announcements in the next few months on that. We are also, looking closely at the C++ code contracts proposal that's under consideration. Our hope is that some of the functionality, one of the nice things about SAL was its extensibility and its composability and its expressiveness. We want to make sure that if there is a code contracts proposal that's being worked on, it meets the needs of SAL so that we can replace some of our custom annotations with standard code contracts. We also want to evolve SAL against that backdrop of, as code contracts become available in the language, we want to evolve our guidance around SAL usage, both internally and externally, and move to a more standard portable implementation. We want to improve the accuracy of the results because as these checks get integrated into the inner loop, it's extremely important that the noise to signal ratio is improved. We've been working consistently on improving the performance. So last year, we worked a bunch with the OS repo here at Microsoft, and we sped up our checks by 45%. And there is a lot of concerted effort that went into it. A lot of heuristics, like if you have been filtering out certain locations, we are not trying to build these expensive control flow graphs. We are not trying to do path-sensitive analysis, which are time-consuming. So we added a bunch of heuristics to make sure that these checks are getting faster over time. We want these checks to be more understandable. So key events that I showed you at the beginning is a great example of that, where you saw that you're not only getting that warning when you're typing in your code, but also the analyzer is dumping out its reasoning. Why it believes there is a bug. We want to customize the results of analysis. So there have been a bunch of features that we have already shipped, like the /external. It's not an analysis-specific feature, but it's for all compiler warnings, you can configure your environment such that maybe you don't want to address the warnings from external headers. So /external flag does just that. We also have rule sets by which you can configure analysis warnings, and we're trying to modernize that experience, making it more intuitive and easy to configure rule sets that is custom to your project. And we are trying to evolve this notion of defaults depending on the C++ target that you are choosing. You can't have one default for every kind of C++ software that you write. So we want to make the default smarter. And we also want to invest in filtering the results. Like the GitHub experience is our first start there, where you saw it's very easy to filter results that is shown in the GitHub visualizer. You can filter results easily there. And we want to add similar capabilities in the native Visual Studio experience as well. Our North Star goal is to make static analysis universally available. One of the things we do realize is when it comes to static analysis, the tooling experience is inconsistent across the tool chains. You don't get the same kinds of checks across different tool chains. And so one of the projects that we are investing right now in is to see how we can modernize our ASTs, which are the building blocks of analysis, and create this an intermediate program representation that is more stable than the underlying compiler. I'm hopeful that in the future we will be able to create a shared code analysis experience across all the other tool chains as well. That's a North Star that our team is looking into. There are a few ways you can connect with us. You can reach out to us using the Visual Studio feedback for feedback and suggestions. You can contribute. We take a lot of suggestions on checks or fixes. Even if you can, contribute to tests or ideas, bug reports, we welcome any kind of contribution. A lot of the checks we work on is heavily guided by the feedback from the community. And you will see that when we blog about these, we acknowledge these community contributions. And that's definitely a big part of the prioritization for us. So do keep that feedback coming. Follow the C++ team blog. This is where we make most of our announcements. And we have a bunch of resources that you can go over. There is first, I left you with a link on the GitHub Actions. If you want to read about code analysis overview for C++, there's a link to that. There's a link to ClankTidy. ClankTidy is a great linter that we have integrated both inside of Visual Studio and very recently inside of VS Code. If you want to contribute in Microsoft GSL, I have a link to that as well. If you haven't checked out CPP core guidelines, do check that out. I have a link to that. And if you're curious to write your own GitHub Actions analyzers on GitHub, there is a pointer to the static analysis results interchange format, or SARIF, which is a JSON format that your tools can produce, and that makes it really easy for you to integrate that tool inside of GitHub. That brings me to the end of my talk. Thank you. Right. I see a question from Sai here. Maybe I can take that.
Yeah. So thank you so much for your talk. Yeah, I think one thing which is very useful for me, especially, is the compiler explorer support. I quite often like to make little samples or prototype things on compiler explorer, and having the static analysis support as well as the nether support for execution on MSVC toolchains as well on compiler explorer is super useful for me. So yeah, we have a few questions so far. Feel free to keep questions coming. We're good for time, so we can answer a bunch of questions. So we have, how do you enable the static analysis in Visual Studio?
Sure. Right now, static analysis is enabled by default. As you are working in a C++ project, it runs in the background, and it shows results as green squiggles in your project. So you don't have to take any explicit action to be able to analyze static analysis, to be able to turn on static analysis in Visual. It's just on by default. You just need to pay attention to the green squiggles. As you hover over them, you will find what they are telling you and then take some action on it.
Cool. And which rules will be enabled by default? All of the rules, or are there ways to enable and disable different rules?
Right. So by default, we have this notion of Microsoft native recommended rules, which is a subset of the rules that we ship. It's not all the rules. Definitely, we are trying to prioritize rules which are more I would say which tend to find more bugs in real world code. And so you will find a subset, but there are ways for you to go. If you go to your project, and you can go to your code analysis tab inside of your project menu, you can select whatever rules you want to customize for your own project. And one of the things we realize is the notion of default can vary, because somebody who is writing a modern C++ app will have a different notion of default than somebody who is targeting device driver, for example. So one of our priorities is to evolve that story, and instead of having one notion of native recommended rules, we want to slice it up by depending on the C++ target that you are writing your code for. So in the future, stay tuned for improvements in that that area.
Yeah, makes sense. And how about if someone's wanting to run static analysis tools from the command line or from other tools? How would they go about that?
Yes, we have a blog. I'm happy to share that link to that blog later on in the chat, but we do have a blog on how you can enable static analysis in other, not just Visual Studio command line, but other build systems. Essentially, we are driven off the compiler. So you have to add a few options to the compiler. And the blog goes into the details of how easy it is to configure that in other build systems. And I would be happy to post a link to that later on in the chat window.
Cool, perfect. Any other questions? Feel free to add them to the public chat on Learn TV, and we'll be able to answer them live. What are you most excited about coming next in static analysis?
I think what really keeps me excited about the next set of features that we are working on, like I said, is the next set of safety checks. So it's great to see, when we get these reports from the security teams, and they send us, hey, like these defects have been caught in production software. That's really exciting for us. And I feel like it kind of keeps the motivation going. What also excites me is this possibility of building this consistent tool in experience across tool chain. That's an ambitious project, and there is a lot of unknowns at this point in time. But I see a lot of commitment and passion from not just the analysis team, but also the compiler team and the community at large, in working towards that platform and making C++ an even safer language to use. So I think I would say those are like two exciting areas for the team. And making this part of inner loop, that's also something that we often overlook. Like we keep investing on on the checks, we keep investing on building these platforms, but it's super important to also be able to make these checks discoverable and expand our surface area. So we have we can do more in GitHub. Right now, our experience is only targeting CMake, for example. So maybe we want to do that for MS Build as well, MS Build projects as well. We want this to be like integrate. Right now, we have in-house solutions of integrating this as part of like Azure DevOps. So we want this to be easily integratable to like any build system that you're using, and not just Visual Studio, but also your PR loop. So we want to like blog about like our story on how we, for example, for the US regulatory requirement, we did a lot of effort in putting this in the inner loop for our own developers. And I think there are useful learnings we can share that maybe other teams can benefit from. I mean, it's really easy to integrate this, and we should be also investing there. And that's an exciting thing for the static analysis team, to make it more discoverable and easily integrated into the inner loop.
Yeah, for sure. Okay, I'm not seeing any other questions. I got one other of my own, maybe on a slightly different note. You talked about trying to get static analysis, which is cross toolchain. How do you see general compiler errors fitting into something like that? Do you think they would factor into that kind of cross toolchain reporting system, or would this be a different kind of thing?
Yeah, in my mind, I think the line is going to get blurry, because if the abstraction that we are working on takes off, then you can do a lot of semantic analysis in your program, and you can use an abstraction that is far away from the compiler. So the beauty of that is the tool chains might change underneath, but your abstraction is going to be relatively stable. So at that point, the kind of errors that you detect may not be just tied to analysis errors, but you can also, compiler warnings are mostly, implementing some dialect from the standard. You could also do that in that abstraction. So I think the line is going to get blurry, because you may have some errors which are closer down using the tool chain that you're using, but you can definitely have some errors which are implemented in that abstract layer. So that's something that will happen organically, and the line is going to get blurry. Like we'll probably have a more integrated experience, and right now I think analysis is like compartmentalized. Like you have first the batch compilation with all the errors, and then you have another pass where analysis runs with these additional checks. And I think that line is going to get blurry, and it's a good thing.
Yeah. All right, great. Well, thank you very, very much for your talk, and we'll see you next time, maybe.